This is part 3 of the Module 8 lecture. Here we're going to now introduce another important concept, which is the type of error in experimentation. So remember, we're trying to estimate the population mean, or a population parameter in general. Therefore, that population parameter is not known. And the decision about the null hypothesis will rely on the sample statistic that we calculated. And because of that, there is a possibility that we may make the wrong decision about the null hypothesis. And that's because of the sampling error associated with the sample statistic. So, in this table summarizes the errors that one can commit. So the experimenter's decision using the sample statistic could be to not reject the null hypothesis or to reject the null hypothesis. And here on this right side of the table, the actual situation could be that the null hypothesis is true or that the null hypothesis is false. So if the experimenter decides not to reject the null hypothesis and the null hypothesis is true, the experimenter has made the correct decision. However, if the null hypothesis is false, then the experimenter has incurred on what is called the type 2 error, where he or she did not reject a false null hypothesis. Now, let's say that the experimenter's decision is to reject the null hypothesis. Well, and if the null hypothesis is true, then the experimenter had committed the type 1 error because he rejected a true null hypothesis. However, if the null hypothesis is false and the experimenter rejected the null hypothesis, well, he or she made the correct decision. Now, another important concept, well, the first thing is to realize that there are two possible errors that we can commit when we are testing a hypothesis. Also, there are probabilities associated with each of these errors. So alpha is the probability of the type 1 error. That is the probability of rejecting the null hypothesis given that the null hypothesis is true. This is the significance level, or sometimes called the risk level. And as you can remember from Module 7, this is the complement of the confidence level. The second probability for the type 2 error is called beta. So this is the probability of not rejecting the null hypothesis when the null hypothesis is false. And the complement of this probability is 1 minus beta is called the power of the test. In our course, we will not talk about the power of the test, but this is the criteria to determine the minimum sample size in most of the statistical applications. Now, I included a couple of mnemonics that I learned from someone, and they help you remember what the alpha probability means or represents. So A stands for alpha probability, R for reject, T for a true null hypothesis. And this other mnemonic called BAF is B for beta probability, A for accepting, and a false null hypothesis. Now, I wanted to emphasize that we're not using the word accept. Here it works out because of this mnemonic. But let me show you an example as to why we don't say we accept the null hypothesis. So consider this case of a right-tailed test. So where the population mean is claimed to be less than or equal to some value mu sub 0. Under the alternative hypothesis, the mean is bigger than that known value mu sub 0. So if we look at this diagram right here and look at the observed value of the statistic, you see it's pretty close to the null hypothesis. I mean, very close to the mu sub 0 value under the null hypothesis. For that reason, we will not reject the null hypothesis. And also, you will see, and you need to notice that the decision to reject the null hypothesis relies on the value of mu sub 0. Because if you notice, we don't say anything about what is the actual mean under the alternative hypothesis. We refer to the known value of mu sub 0. Now, let's assume that we know the value of the mean under the alternative hypothesis, and let's say that that's mu sub 1 as shown in this diagram. So now you can see that the observed value of the statistic is not too far from mu sub 1. So this is a likely value for this distribution with mu sub 1. But this mu sub 1, or in other words, the mean under the alternative hypothesis, is never known. So when you reject or do not reject the null hypothesis, does not necessarily mean that this value mu sub 0 is a true mean. We don't know. I mean, we see how far it is from mu sub 0, and then we decide whether we say that this is a plausible value for the population mean or not. But we never really know if it is a value that belongs to this distribution. For that reason, we say that we fail to reject the null hypothesis, or that we do, and the null hypothesis is not rejected. We don't say we accept the null hypothesis, or we say the null hypothesis is the truth, so that this mu sub 0 value is the actual value of the mean. We don't say that because we don't know. So we use this type of language. All right. And the next concept to talk about is the significance level. And the significance level is the level of the acceptable probability of making the type 1 error. That level of significance or risk level is established by the experimenter, the person performing the experiment. That means you, if you're testing a hypothesis, you establish the value of alpha. Now, for practical purposes in our course, alpha will be given to us. But remember, in practice, this is determined by the person performing the experiment. All right, there are two approaches to make a decision about the null hypothesis. One is that we call the critical value approach, and another one, which is equivalent, which is different, is the p-value approach. In the critical value approach, we determine the critical value of the test statistic using the significance level. And then we compare that value, that critical value t sub c, with the calculated value of the test statistic t observed. That's based on the statistics from the sample. And through that comparison, we make a decision about the null hypothesis. Now, if we decide to go with the p-value approach, then the probability alpha, or the probability of the type 1 error, is compared with the probability of obtaining an observed value or a more extreme value of the test statistic, assuming that the null hypothesis is correct. This is the definition of the p-value, the probability of obtaining the observed value or a more extreme value of the test statistic, assuming that the null hypothesis is correct. And so we compare this probability with the p-value, which is another probability, and we just make a decision about the null hypothesis. So we're going to look at these two approaches a little later. But before I do that, let's talk about how we select the probability distribution. So the sample mean and the sample standard deviations are calculated from the data in the sample. So, and we would use the t-probability distribution with n-1 degrees of freedom if the observations in the sample are independent, and if we replace the population standard deviation with the sample standard deviation, and the sampling distribution of the mean is normal. These are the same conditions that we used in Module 7 to decide that the correct probability distribution to use is the t-distribution. So once you select the t-distribution, then that implies that this is the definition of the test statistic, where the x-bar observed is the sample mean, mu sub 0 is the mean of the population under the null hypothesis, S observed is the standard deviation calculated from the sample, and n is the number of observations in the sample. So all this information is known from the problem, so we can calculate the observed value of the test statistic. All right. So the critical value approach to test a null hypothesis, as I said, we determine the critical value using the value of alpha. So that's something we did in module 7. So we will use alpha, go into table 5, and find the critical value of the t critical value. Then we're going to use that critical value to determine what we call the rejection region and the non-rejection regions. So if the calculated value of the test statistic lies in the rejection region, then the null hypothesis is rejected. If the value of the test statistic lies in the non-rejection region, well, we will not reject the null hypothesis. All right, so where the rejection regions and the non-rejection regions are depends on the direction of the test. So if we have a left tail test, then the rejection region is on the left side of the critical value. And you can see alpha determines the critical value. So if the observed value of the statistic falls in the rejection region, we reject the null hypothesis. If it's a right tail test, then the rejection region is on the right side of the critical value determined from alpha. If we have a two-tail test, then we have two rejection regions, one on the left tail and one on the right tail, and these t critical values corresponds to the alpha value divided by 2. Now I put the Excel equations here for each of the cases so that you can calculate the exact value of the critical value if you like to use Excel. All right, the second approach, the p-value, is compared with the significance level alpha. So if the p-value is smaller than alpha, the null hypothesis is rejected. If the p-value is larger than alpha, the null hypothesis is not rejected. And you can use this mnemonic that says that if the p-value is low, H0 must go. And I'm showing you the p-value because this is the modern way to test hypotheses. Every paper that you read is quoting p-values. So you need to understand the p-value methodology because this is what you're going to find in practice. All right, the value of the test statistic, t observed, is used to find the p-value. So the p-value is defined by the calculated value of the test statistic. And how the p-value is found is determined, again, by the direction of the test. So if we have a left tail test, then the p-value is the probability to the left of the calculated test statistic. And again, I put the Excel formulas here so you can calculate the exact p-value. If you have a right tail test, then the p-value is the probability to the right of the calculated test statistic. Or you can use the Excel formula to find the exact t-value. When you have a two-tail test, then the p-value is 2 times the probability to the left or the probability to the right, or you can think of it of summing the probability on the right-hand side plus the probability on the right-hand side. And that's the probability to the left of the negative value of the t of the calculated test, the calculated value of the test statistic, or to the right or the positive value of the test statistic. So in here, because we never know where the observed value is going to be, the p-value is for both tails. And so the p-value is just 2 times the probability to the left of the t observed value. And again, you can use this Excel formula and you can find the exact probability, of exact p-value. We're going to see how to do this in subsequent examples. So I'm going to stop here. In the next section, we will discuss several examples and see how this is done.